Okay, molar mass. So chemists often want to know how many atoms are in this sample. We want to know this because atoms react with other atoms. Chemical reactions involve reactions between individual particles, and so the numbers of particles are important. So there's too many atoms in anything large enough to see for anybody to be able to count. Because counting a mole of something, even the fastest you could possibly count, would take more than your lifetime. So that's not going to work. So we count them by weighing. And we do this with ordinary sized objects as well. If you have oranges, you can estimate the number of the oranges by weighing them and knowing what the average mass of an orange is. And we use units that are counting units for real-sized objects. And the dozen is probably the most familiar. A dozen objects is 12 objects. Does it matter what the objects are? No, a dozen just means 12. You can have a dozen donuts, you can have a dozen eggs, you could have a dozen sandwiches, right? I don't know why I'm talking about food. I did eat. A dozen is 12. Gross is another unit. A gross of objects is 144. That's a weird number. It's a dozen dozens. That's where that came from. Another one that we see sometimes is one ream. A ream is 500, usually used for paper. A ream of paper is 500 sheets of paper. And when you buy a ream of paper, I've never personally counted to see if there were actually exactly 500 pieces in there. Do you expect there to be exactly 500 pieces? Well, ideally there would be, right? But if you got 502, would you complain? No.
I got $4.99.
If you got $4.99, but see then, counting 500, you could easily make a mistake, right? So nobody really worries about that. I don't know why I went off on that tangent. Okay, so in chemistry, a dozen is still too small. Even a gross or a ream is too small to be useful. And so we've got our own unit, and it's called the mole. So you could think of this as the chemist's dozen. It's a counting number. It just means a particular number of things. And it's just kind of an odd number. We call it Avogadro's number because Avogadro was the scientist whose work led to this idea. A mole is 6.02214 times 10 to the 23rd particles. That is an incredibly big number. It's a 6 with 23 zeros after it. It's just mind-boggling. So 1 mole of anything is 6.0214 times 10 to the 23rd units of that thing. A mole of cars, a mole of people, a mole of planets, and you could talk about any of those.
It's crazy because when you're solving some of these, you'll get like, thousands, 10,000th of a mole, and then when you calculate the particles, it still raises like...
Right, yeah, so even if you had like 10 to the minus 4 moles, you still have an outrageous number of particles. There's some analogies, I'm probably going to mess them up, but they'll still be in the ballpark of correct. Of if you had a mole of marbles, it would be the size of the moon. There's a whole bunch of these, they just kind of blow your mind. There's another one, a mole of, and I forget what it was, that might have been marbles too, but it would cover the face of the earth to a depth of like 3 miles or something. Pennies.
300 meters.
So it's just crazy. We cannot grasp how big of a number this is. We just can't. My kids had a book, How Much is a Million, that talked about, well, if you had 1 million strands of spaghetti and it would reach this far, and that one was mind-boggling. 1 million, that's nothing compared to this. This number is one of the reasons why we need to be able to do scientific notation, on our calculators because there's no other way to get this into your calculator. So a mole is a useful quantity because when we have this many atoms, we have a reasonable, usable amount of stuff. So 22 copper pennies has about 1 mole of copper atoms. So 22 pennies, you can hold that in your hand. It's big enough that you can see it and manipulate it, small enough that it's, easy to work with as well. A tablespoon of water has approximately 1 mole of molecules. So a mole of a substance is a useful sized amount of it. So how did that number come about? This relates to the definition of the atomic mass unit, which probably seemed a little weird. Remember, the atomic mass unit was 1/12 the mass of a carbon atom with a mass number of 12. So 6 protons and 6 neutrons. The value of the mole is the number of atoms in exactly 12 grams of pure carbon-12. How much does 1 carbon-12 atom weigh? 12 atomic mass units, because the atomic mass unit was defined that way. So 1 carbon-12 atom weighs 12 atomic mass units. A mole of carbon-12 atoms weighs exactly 12 grams. So, and here we see 6.022. That's how we usually use it. You should memorize that number. We're going to use it a lot. Any question?
Do we still use it in the same way, like in 3A, when you want to convert to like molecules or atoms or like non-specific things? You use the
Yeah. So this can be used with any particle. So it can be used with ions or molecules or atoms. Yeah. So the mole gives us the relationship between the mass in grams and the number of atoms, Avogadro's number. Just a little aside, because I'm doing lots of tangents today. So this is kind of a special number to chemists. And so, the math people have Pi Day, right, on March 14th, and the Star Wars people have May the 4th. Be with you, right? So the chemists have Mole Day. Mole Day is October 23rd, 1023. It's coming up. So, whoops, I didn't mean to do that. Mole Day. So it's 1023, technically celebrated from 6:02 a.m. to 6:02 p.m., right? So that's Mole Day. So I'm a chemist, and my husband is a chemist, and so one of the coolest things that happened in our lives is our 4th child was born on Mole Day. And he weighed 10 pounds, and he was 23.5 inches long.
Do you guys know the calculations exactly?
No, we didn't. It just happened that way. It would have been really cool if he could have been born at 6:02. It was more like 8:30. So there's limits to what can be done. But so he's our mole baby, and I think my husband asked the question, should we give him the middle name Avogadro? And then we quickly decided no. His middle name is named after a Nintendo game, so that's better.
What is it?
Yoshiaki.
Oh.
Or Yoshi's Story. Anyway, okay. So, converting between moles and atoms. This is just like converting between eggs and dozens of eggs. So, for atoms, we're going to use this conversion factor. A mole of atoms, or ions, or molecules, or whatever you're looking at, 6.022 times 10 to the 23rd atoms. So you can write it 2 factors, one with moles on top and one with atoms on the bottom, or you can turn it upside down. So this is like 1 dozen is 12 eggs. You have to get the numbers with the correct unit. You can't say that 12 dozen is 1 egg. So you can't say that 1 atom is 6.022 times 10 to the 23rd moles. So if you find that you're messing up like that, mentally put dozen in for mole and say, do I have the number in the right place? So let's do an example. A pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? So here we're using dimensional analysis. We're starting with atoms, and we want to know how many moles. And we can do this in one step. I don't think I mentioned it before. The unit mole is only 4 letters long, and yet it has an abbreviation, MOL. The silent E is silent after all, but I think it's dumb because I think it would be better to have an abbreviation for molecule, but there isn't one. Anyway, so MOL, moles, same thing. So we're going to do this in one step. 2.80 times 10 to the 22 atoms. So one step, we've got the unit we're wanting on top and the unit that we need to get rid of on the bottom. And the relationship between moles and numbers of things is Avogadro's number. 1 mole, like 1 dozen, is Avogadro's number of things, 6.022 times 10 to the 23rd. Now get your calculator out and make sure that you can get your calculator to give you the correct answer here. So we've got it all set up. Now we need to get it communicate correctly with our calculator. You want to use the button that your calculator has for scientific notation. I know there are other ways that you can get answers. If you learn how to do it correctly, it is a lot easier in the long run. So it should have an EE button or an EXP button. Sometimes they have a times 10 to the X button. Some of those work great, some of those are a little dangerous.
Do they have a mole?
There's no mole button. Nope. That would be nice. Okay, so you want to put in 2.80 EE22 because that scientific notation button stands for times 10 to the. And when I press EE, it only shows one E on the display. That's okay, don't press it twice. And then I'm going to multiply by 1 if I need to do that, and I'm going to divide by 6.022 EE23. And press equals. And I can predict how many sig figs I need. This has 3 sig figs. This has 4 sig figs. We never want anything that we're using as a conversion factor to reduce the number of sig figs. So it's usually the starting number. So 3 sig figs, 0.0, those don't count. 4, 6, 4. There's 3 sig figs. Write down 2 extras, and then round. 0.0465 moles. Now, if you're having a miscommunication with your calculator, you might have ended up with a really, really big number. Question?
So, moles to Avogadro's number, would that be considered an exact number?
That's a good question. Is this exact? No, it isn't. On an earlier slide, we gave it as 6.02214 times 10 to the 23rd. That's not exact either. Yeah. So it has been determined to more digits, but in Chem 1A, we don't care.
So if the starting number has more digits, then can we use as the sig number 6?
Right, so if this had like 6 or 7 significant figures and I was using 6.022, I'd have to only keep 4 sig figs in my answer. So if you're having issues with your calculator during lab today, is a great time to come and ask me and we'll get it straightened out. It's always your calculator's fault. So we still need one other conversion factor. The mass of 1 mole of atoms. So 1 mole of carbon-12 weighs exactly 12 grams. But what about all the other ones? So the mass of 1 mole of atoms is called the molar mass. So we talked about the atomic mass. That's the mass of an atom, the atomic mass. The molar mass is the mass of 1 mole of the stuff. So An atom's molar mass in grams per mole is the same number as its atomic mass in atomic mass units because of how atomic mass unit and mole are defined. It was done this way intentionally because it's really convenient. So aluminum has an average atomic mass of 26.98 atomic mass units. That's the number on the periodic table. 1 mole of aluminum atoms weighs 26.98 grams. 1 mole of aluminum is Avogadro's number of aluminum atoms. 1 mole of carbon, now this is just regular carbon, it's not just a single isotope. 1 mole of carbon weighs 12.01 grams because there's other isotopes in there. There's carbon-13 and carbon-14, and those up the mass a little bit. Helium, a mole of helium is 4.003 grams. So a mole of each substance, they have the same number of atoms in them, but a mole of aluminum weighs more because aluminum atoms are bigger. If you had a mole of bowling balls and a mole of baseballs, which one's going to weigh more? The bowling balls, because each of the pieces is bigger, right? Any questions? So the molar mass is what we use to convert between moles and grams for an element. So this number on the periodic table, 12.01 grams. That's the mass of 1 mole. And so we can make 2 conversion factors, 12.01 grams per mole or 1 mole per 12.01 grams. You can do that for all of the elements. Depending on which periodic table you look at, there may be more or fewer digits. So here we're saying it's 12.01. If we look at the periodic table on our wall here, it says 12.0108. Is that wrong? There's another one that says 12.011. Well, they're just rounded to different numbers of significant figures. In lecture, I will mostly use molar masses rounded to 4 sig figs because I've got them in my head and it just makes things go much faster. Most of these molar masses are known to more digits. Most of the time in Chem 1A, it really doesn't matter. So you can use all the digits on whatever periodic table you're using, or you can round to 4 sig figs. Never go fewer than 4 sig figs. Because things like chlorine, 35.45, that's almost in the middle between 35 and 36. When you round that, you add a bunch of error. And so you don't want to do that. Always use at least 4 sig figs in your molar masses. So let's calculate the amount of copper in moles in a 35.8 gram pure copper sheet. We can approach this as a dimensional analysis problem. We're given a mass in grams. It's that many grams of copper. And what do they want us to give? Amount of copper in moles, right? So we want moles of copper. We can go between grams and moles in 1 step. That's the molar mass. So 35.8 grams of copper. And I'm going to use 1 factor here. I'm going to put moles on top and grams on the bottom. So the units cancel out. There's no thinking about, do I multiply by the molar mass or divide? Just get the units to work out. Now I need the molar mass, so I go to the periodic table. Copper is 63.55. So 1 mole of copper weighs 63.55 grams. Done. So 35.8 divided by 63.55. I know that my answer is going to have 3 sig figs because of the starting number. So I've got 0.563, and the next 2 digits are 33. The unit is mole, and then I'm going to round 0.563 moles. Any questions? Yeah.
What about the data for the molar mass? Would that be exact also?
Molar masses are not exact. The only one that's exact is carbon-12. Any other questions? This is a very, very important type of calculation. So now we have what we need to count atoms by weighing them. So we would have the mass of the sample. We'd convert the mass into moles by using the molar mass for the element, and then we convert moles into numbers of atoms using Avogadro's number. So grams to moles to number of atoms. In every unit conversion path, we need to have a relationship for each arrow. So here, this is the molar mass of the element going from grams to moles. Avogadro's number takes us from moles to number of atoms. So how many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon, and a carat is 0.20 grams. This is dimensional analysis. So we pull out the numbers that we're given. So we've got 1.3 carats. It's not a vegetable.
This one was on the homework.
It might have been. And then we've got this relationship here, but that being in parentheses, we're probably not going to use that to start with. This is probably what we want to start with. And then what are they asking us to find?
The amount of carbon atoms.
Carbon atoms, right? So how to get from carats to atoms?
First, we have to multiply by the 1 carat is equal to.
Yeah, first we're going to use this to get from carats to grams. They gave that to us because that's a kind of a weird one. And then getting from grams to atoms, moles. So anytime you've got these two things and you can't figure out what goes in the middle, oftentimes it's moles. Moles in the middle. Like that TV show Malcolm in the Middle, it's moles in the middle most of the time. So we can convert from grams to moles using the molar mass of carbon, and then moles to atoms using Avogadro's number.
So when you have like 18 karat gold or whatever, what is that?
So that's a good question. What is 18 karat gold? 18 karat gold tells the amount of gold that is in as a pure gold does not make good rings or jewelry because it's too soft. It bends. It's not as bad as Play-Doh, but it bends. And so they make alloys of gold with other metals to make them harder and give them better characteristics. And so 18 karat gold or 24 karat gold, that's going to tell relative how much gold is in the alloy.
So it's like 0.20 grams per something, is that what it's saying?
I don't know.
It's not the same relation.
No, it's not the same relation. So here's our path. That's the hard part. Now we just follow the path. So we've got 1.3 carats. We're going to convert that to grams. So we can put carat on the bottom. Carats are going to cancel out. Another arrow. This one's going to have mole on top because that's next in our path. And we're going to put gram on the bottom. The grams cancel out. Then we're going to get atoms. And we're going to have moles on the bottom. So the moles cancel out. Once you grasp dimensional analysis, it is a beautiful thing. I mean, it's just like, oh my goodness, that makes everything so much easier. If it's still muddy to you, please keep at it. Pester me with questions until it gets clear. So here we've got our grams and our carats. So 1 carat equals 0.2 grams. So 0.20 grams, 1 carat. Here we've got moles and grams. That is the molar mass. We're going to use the average molar mass from the periodic table. 1 mole is 12.01 grams of carbon. Then atoms to moles, always the same, Avogadro's number. And it's so long, it's just, you never end up saving enough room for it. So this number is going to be a really big number, right? Because a 1.3 carat diamond is big enough that you can see. So it's got to have tons of atoms in there. Not tons, literally, but gazillions. So my calculator is showing me 1.30368 and a bunch of other stuff. And then it's showing me E22. Different calculators do it differently. The E22 is the way my calculator says times 10 to the 22. My starting number had 3 significant figures. This had, sorry, 2. That is a 3, but yeah. 2 significant figures, 2 significant figures, 4 and 4, so this is going to have 2. Did anybody else get that same number? Yeah? Okay. Because it just seems a little coincidental that it was 1.3 and it's still 1.3. So that's going to be 1.3 times 10 to the 22 atoms. Really, really big number, but we expect that. Sometimes students do problems like this and they end up with like 5 times 10 to the negative 42 atoms. If you have a negative exponent, that's less than 1 atom. You can't have less than 1 atom. You can have 1 atom or you can have 0, but you can't have part of an atom. So look at your answer and see if it makes any sense at all. Any questions? Do one more. A titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. So this is going to combine using Avogadro's number and molar masses with problem solving, critical thinking. So probably not immediately obvious what to do here. So we're going to take the numbers out and write them down. So 2.86 times 10 to the 23 atoms. At this point, we don't always have to write down what element it is, but it never hurts. And in this problem, we're going to need to know what the element is. So this is atoms of titanium, and titanium is Ti. And then there's a question in there, and then there's another number, 4.50 grams per cubic centimeter. So I want to write that as a vertical fraction. That's the density of the titanium. So I collected the information I was given, then I have to find out, what am I supposed to find? The edge length of a cube. Well, let's call that L for length. And then we're like, what the heck? Okay, this is a problem. We're going to have to use an equation along with dimensional analysis. Sometimes it helps to draw a picture.
You're going to use mass or volume for this?
Yeah, we're going to use the density. Okay, so there's my cube. Cubes have the length of each side the same, right? The volume of a cube equals the length times the length times the length cubed, right? So if I want to know the length of this side, I could find that if I knew what the volume was, right? To find the length, I would take the cube root of the volume. So here, I need to find volume. The conversion factor here is an equation. It's not just some fraction thing. We actually have to use the equation. So now I'm back to, how do I get a number of atoms to a volume? Well, I was given this, grams per cubic centimeter, the density. Density relates mass and volume, right? So if I had the mass, the number of grams, I could use the density to find the volume. Okay, so I'm getting closer. So there's atoms, there's grams. I'm missing something in the middle, moles in the middle. So I can convert atoms into moles, and I can convert moles into grams. Yes?
So if you went from atoms to moles to grams, and then just threw in density at the end, but inverted, could you then take the cube root of that answer or no?
Yeah. It's just a different way of thinking about exactly what we're going to do. So we're going to start with our number of atoms, 2.86 times 10 to the 23rd atoms. And I'm going to convert to moles. And then I'm going to convert to grams. And then I'm going to convert to cubic centimeters. So moles to atoms is Avogadro's number. Grams to moles is the molar mass of titanium, 47.867. And this last term is the density. So bless you, sneezy person, you were talking about getting to grams and then throwing in the density, right? So here's the grams.
Yeah.
You do all this, and then we're using the density to convert to volume. So cubic centimeters would be on top, and 4.50 grams is on the bottom.
So everything would cancel and be left with cubic centimeters.
Right.
So you take the cube root of that answer.
Yeah, so we need to find out what the number is that belongs with this. So we've got 2.86 EE23 divided by 6.022 EE23 times 47.867 divided by 4.5 equals. I'm going to think about sig figs. I should have 3 because this number of atoms and the density both had 3 sig figs. So 5.05 is my 3 sig figs. Write down 2 extra digits. That's my volume in cubic centimeters. To find the length, I'm going to take the cube root of that. And depending on your calculator, that's going to take different forms. I have a button on mine that allows me to choose which root I use. So on mine, I'm going to say 3, and then that box root of the thing button. It looks like this. And then I put the number that goes inside, 5.0518, and I press equals. So the length is equal to the cube root of 5.0518 cubic centimeters. When I take the cube root of cubic centimeters, I get centimeters. And so I'm going to get 1.7158 centimeters. And I'm going to round that to 1.72 centimeters. If your calculator doesn't have that button, it should have a y to the x button. You can raise it to the 1/3 power, and that'll also get you the cube root.
I got the same answer, but some of my intermediary answers were off by a few. Like you got 5.051, I got 5.053.
So if your digits are a little bit off, it might be because of what exact molar mass you used. Mm-hmm.